Hello everyone, it's give my great pleasure to present to you the most recent of our research activities at the Hashemite University in Jordan, which I summarized under the title Robust Path Following Controllers for Quadrotor and Ground Robot. We know that unmanned ground and aerial vehicles have been widely discussed in recent years. They are useful in many civil and military applications. Their ability of keeping humans away from danger and hazard environment, as well as their flexibility and reliability, made them the means of choice in a variety of applications ranging from agriculture, industry, and research and rescue operations. In many applications, such as surveillance, it is required that a quadrotor to follow the movement of a ground vehicle autonomously. This is a great challenge due to the complexity and the nonlinearity of the robot's dynamics and kinematics models. Moreover, uncertainties and external disturbances affect the performance of the controller. Therefore, the design of a stable and reliable trajectory controller and path planning has been the main objective of scientists and researchers. For example, PID control schemes were investigated in many works for a quadrotor and for a differential drive robot to stabilize the robot and follows the desired motion commands. In another side, a linear quadratic regulators were tested in other works to give better performances. Nevertheless, linear-based controllers do not show asymptotic stability. For this reason, many researchers used sliding mode controllers to achieve system stability in the presence of disturbances. Also, the sliding mode controller combined with an adaptive law based on certainty equivalence principle was used to deal with uncertainties in a quadrotor motion. It is known that sliding mode controller schemes use a sine function to switch between modes or sliding surfaces, which leads to chattering phenomena. Nonlinear H-infinity controllers were proposed in different approaches to deal with external disturbances and track the reference trajectory for the quadrotor and the ground robot. The disadvantages of this technique include the high level of mathematical understanding needed to apply it successfully and the need for a reasonably good model of the system to be controlled. In tracking a ground target, a vision-based fuzzy controller for a quadcopter is found in literature, where the fuzzy control doesn't require an accurate model. For the same purpose, a direct adaptive neural controller was designed to control translational motion of the quadrotor. However, such controllers are computationally expensive, which might lead to system instability. On the other hand, backstepping controllers offer an alternative. They were developed for stabilizing nonlinear dynamical systems using a recursive algorithm that links the Lyapunov function with the design of a feedback controller, which guarantees the global asymptotic stability of strict feedback systems. In this work, backstepping techniques are used to solve both trajectory tracking and stabilization problems in a quadrotor and a two-wheel differential drive mobile robot. This work also introduces a potential field method for motion planning of a quadrotor to track a moving ground robot. The planning controller produces an attractive potential force as a function of the relative position and velocity of the target with respect to the quadrotor. The performance of the control systems were evaluated experimentally. The backstepping controller in this work is used for control of nonlinear process or operation. The controller is adapted for its capability to solve the stability problem inherent in a quadcopter. And most importantly, the control system guarantees a global asymptotic convergence of the quadrotor position to the desired path. Unlike most other control systems that separate between the translational and rotational dynamics, the backstepping controller integrates between both dynamics in one control loop. The objective of this controller is to ensure convergence of the quadrotor position to desired path. The control law generates four actuating signals, one as a thrust and three torques, and a timing law for the path parameter that guarantees convergence of the quadcopter position to the desired path. The system produces the thrust control law based on the desired thrust value and the thrust direction. Moreover, the system calculates the torque control law based on the calculated angular acceleration. The backstepping controller defines four error vectors, which are calculated to be considered in the control law, and the current positions of the quadrotor and the rotational angles are provided using an indoor motion capture system. Furthermore, fused information from the motion capture system with an inertial measurement unit, we can get estimation for the linear and angular velocity. The ground robot side, the aim of the control law is to minimize the tracking error between the reference trajectory and the current position. The control law is established by considering the linear and the angular velocity as control inputs. The proposed control law is given as presented here. The aerodynamics is required to complete the control law, which is defined by the difference between the reference trajectory and the current position. Then by mapping the robot kinematics and the motor motions, we get the required speed of each motor. After that, the motor model with a PID controller is considered for motor voltage regulation. The robot states, such as positions and orientation, are provided by an indoor motion tracking system, or they can be estimated using an accurate odometry. Finally, the desired positions and velocity of the robot are defined by a motion planning system. Here in the motion planning system, the goal of this system is to allow the quad rotor to track a moving ground robot. The system generates a virtual potential attractive forces for a real-time and dynamic trajectory, which gives the quad rotor the ability to track a target. The attractive force model is provided by the relative position and velocity vectors between the quadrotor and the ground robot. Here the value A1 is the first force component that pushes the quadrotor to the target and reduces the distance between them. A2 is the second component that keeps the quadrotor moves at the same velocity of the target. This model is a function of delta P and delta V, which are the relative position and relative velocity of the quadrotor with respect to the target ground robot, respectively. The updated required position of the quadrotor is calculated at time step k within a short time interval delta t using the body motion equation. The proposed control systems were implemented on a quadrotor and the ground robot for real-time experiment. The figure demonstrates the robotics platforms with a motion capture system that provides real-time positions and orientations. The robotics system solution is provided by Quansor. In the experiment of this work, a quadrotor was adopted to automatically track a moving ground robot, which is the target. The ground robot was provided by a predefined path. In the first experiment, the main drone must reach the stationary ground robot. The quadrotor starts moving at a distance of about 5 meters from the robot's position. The quadrotor here is very responsive and tracks the robot position effectively and reached its position within 5 seconds. In the second experiment, the quadrotor tracks and follows a moving robot. The potential field motion planning system provides the quadrotor with the appropriate position information that allows it to track the target effectively. The motion planner was updating position information at 10 Hz. The experiment here shows accurate and robust path following with mean errors equal to 4.3 centimeter. This paper discussed the experimental evaluation of the quadrotor motion while tracking a moving ground robot. Backstepping controllers were adopted for each robot stability and trajectory tracking. Furthermore, a potential field motion planning was proposed for the quadrotor due to its mathematical elegance and simplicity to determine the path in minimum computation time. The potential approach was generating an attractive force that was pulling the quadrotor effectively toward a moving or stationary target. The experimental results presented a robust, smooth, and responsive motion of the quadrotor to track the moving robot. The extension to this work will consider obstacles in the path of the quadrotor. Therefore, the motion planning system will include a repulsive force that help the quadrotor to avoid stationary or moving obstacles. This is all I have for today. I hope there will be more meetings. I also hope that this session will be a key to research collaborations. If you have any questions regarding research details or you are willing to collaborate, please don't hesitate to contact us.